Equations of planes. So a plane in three-dimensional space can be completely determined by a point and two non-collinear vectors that kind of outline the sides of the plane. So planes drawn on a 2D surface are usually represented with parallelograms. In order to write the vector equation of a plane, we just simply extend our vector equation for a line to include the other direction that the plane goes. So this a representation of r starting at some point x, y, 0, it's going to move s in the a direction and t in the b direction. So let's write a vector equation for the plane that is defined with these following direction vectors. This is pretty straightforward. We're just going to say that this plane is starting at r. We're going to start at this point 5, 4, -3, and then we're going to move in the direction of A. We're going to move 2, -3, 1, and then also in the direction of B, -1, 6, -7. So we're starting at a point and we're moving in two different directions. And these letters A and B, they don't have to be A and B. They're most often S and T. Doesn't really matter. The parametric equations for a plane are also easily determined from the vector form of the plane in general, such that x is represented by a starting point in x plus some movement on A and then some movement on B. And the same thing is true for y and z. So let's convert the one example above to a parametric equation. So if we were to convert that to a parametric equation, we would say, okay, I have these components, x, y, and z components. In that example, x started at 5, y started at 4, and z started at -3. And then we moved 2 in the a direction and -1 in the b direction. We moved -3 in the a direction and 6 in the b direction on y, and 1 in the a direction and -7 in the b direction on z. You can just look back at that and see that those are my direction vectors. These are my parametric equations. Okay, let's try to find the vector and parametric equations for the plane that's defined by the line r 1, 1, 1 plus s -1, 1, 0, and also this point p 1, -5, 9. So in order to do this, I'm just going to quickly kind of sketch this out. So let's say that this is the point on my plane 1, 1, 1. And I know for sure that this line is going in this direction, and we'll call this direction -1, 1, 0. But I also know that I'm going to include this other point, and this point is the point 1, -5, 9. Okay, so I have one direction vector already, but I need to get another direction vector. So I need to actually find the direction from in blue here. I need to find this direction. So I'm going to work that out. So from R to point P, what is that direction? Well, from 1 to 1, that's 0. -5 take away 1 is -6. And 9 take away 1 is 8. So my second direction vector is 0, -6, 8. I want this to be as simplified as possible, so I'm actually going to reduce that to be, I can factor out a 2. That's going to be 0, -3, 4. Okay, now I have two direction vectors and a point that is on the plane. So I'm going to say the plane has the point 1, 1, 1, goes in this s direction, -1, 1, 0, and it also goes in this t direction that I just found of 0, -3, 4. This is the vector equation, and I can also find the parametric equation, where I break down the components of x, y, and z. Okay, so x starts at 1, y starts at 1, z starts at 1. I move negative s. I move positive s. I don't move any s. I move no t. I move negative 3 t's. And I move positive 4 t's. This is my parametric equations for this plane. Let's figure out if point P1413 lies on the plane that is defined by these points A, B, and C. Okay, let's draw a little diagram just to help us out. So A, B, and C. So here's A, and here's B, here's C. So this is a plane defined by vector AB and AC. Okay, and actually there's a mistake in the question. I need a -1 there. All right, -1, take away -1 is going to be 0. 1 take away 3 is -2, and 0 take away 8 is -8. That can be reduced. I can factor out a -2 there to give me 0, 1, 4. And then from A to C, I go from 4 down to -1. So that's a movement of 5. 1 minus 3 is -2, and 1 minus 8 is -7, and that cannot be reduced. But now I can write the equation of my plane. I'm going to start from point A, doesn't matter, but my brain likes starting at A because that's how I've drawn it. And I'm going to move in the S direction 0, 1, 4, and in the T direction 5, -2, -7. Okay, I'm going to convert to my parametric equations here, x, y, and z. Okay, the x is starting at -1, the y is starting at 3, and the z is starting at 8. And then x is not moving in the S, but it is moving 5 in the T. 3 is going 1 in the S and -2 T's. And then 4S and -7 T's. And so what I want to know now is there a point where I'm going to get 14, 1, and 3 for the same values of S and T? Okay, so we have a little bit of a head start here because I don't have an S in this first one. It's kind of a bit of a cheat. And we'll look at examples later where we have to do more work like solving systems in order to get this. But is the point 14, 1, 3 on this line? Well, I'm going to say, okay, I don't have an S movement here, so I'm going to put 14 into my first line equals -1 plus 5t, 15 equals 5t. Okay, so this is probably happening, if it's happening at all, when t is 3. Plug this guy into line 2, doesn't matter. So 3 equals 8 plus 4s minus 7 times 3. 8 minus 21 and is -13. Positive 13 on the other side, so that's going to be 16 equals 4s. So s equals 4. Okay, so if t equals 3 and s equals -4, does z give me, or does the y give me the output of 1? That's my last check here. That's what I need to know next. So the equation for y is 3 minus s minus 2t. Does that equal -4? Does that equal 1? Well, 3 plus 4 minus 6. Yeah, that does equal 1. So that is proof. That's good.